Alright, this is your video on average atomic mass. Average atomic mass. Now, an average atomic mass is the number that is actually on your periodic table tiles, sometimes called the mass number. So if I have, say, carbon and the atomic number is 6, the atomic number, again, represents the number of protons. The mass number represents the number of protons and neutrons within a particular element or a particular atom. Now, hopefully when you look at this and you go, well, 12.01, how can you have 0.01 of a neutron or 0.01 of a proton? And of course the answer is you can't, because this is actually, the mass number is an average mass, okay, and it is a weighted average. With this particular element, carbon, okay, we have 3 different isotopes. We have carbon-14, we have carbon-13, and the most predominant, carbon-12. Okay. Obviously, if your average is closer to one of your isotopes, then that could weigh into as the abundance of that particular isotope. So carbon-12, since the mass is 12.01, it would, show that carbon-12 is by far the more abundant element. Now, of course, this isn't always 100% true, but it's a good characteristic and a good quality to look at when you're trying to solve for these average atomic masses, and it can kind of help you predict your possible answers when you are doing problems like the one that I have written on the board right now, or printed on the board right now. Okay, so rubidium has 2 common isotopes. It has rubidium-85 and rubidium-87. Okay, the abundance of rubidium-85 is 72.2, and the abundance of rubidium-87 is 27.8. Now, just looking at that piece of information right there, I can kind of, in my head, predict, well, I'm probably going to be closer to rubidium-85 than I am going to my final average atomic mass, which is what I'm looking for, right? I know because this is in higher abundance than this one, I know that that average atomic mass is actually going to be closer to 85 than it is going to be to 87. Now, there's 2 pieces of information that you need when doing an average atomic mass or doing a weighted average. You need to know the mass of that particular isotope, and you need to know the percentage or abundance of that particular isotope. Okay, so in this case we have 2 common isotopes, and that was 85, rubidium-85, okay, which you normally write like this, right? Rubidium-85, and we have rubidium-87. Okay. Now I'm just making a table just to maybe make things look a little easier, right? And the abundance of rubidium-85 is 72.2%. 72.2%. And 87 is 27.8%. Okay? Now when you're working with this, you're always going to want to either do one of 2 things. One, do all the calculations and then divide by 100 to get rid of these percentages, or do what I tend to do is I just get rid of them now. So I'm going to take this number and I'm going to divide by 100, and so the abundance number that I'm going to be dealing with, or in this case we call it a frequency, is going to be 0.722, and then this one will be 0.278. That's my abundance frequency, okay, for those particular isotopes. Next, the other information I need is the mass. Well, it's really simple. The mass of rubidium-85 is 85 AMUs, right? AMU stands for atomic mass unit. So when I look at rubidium-85, I know that the mass is 85 AMUs. So I'm going to put 85 here, and for rubidium-87, I'm going to put 87 right there. Now my next step is to multiply that 0.722 times 85, and I'm going to end up with 61.37. And then I'm going to go 0.278 times 87, and I'll get 24.186. Now, if you're looking at this going, well, Mr. Rapp, you're not really following sig fig rules. Here's the thing. Because these are all exact numbers, okay, these percentages are considered exact numbers, and the masses are considered exact numbers because they were measured from the sum of the protons and neutrons. Okay, there's no real place for sig figs right here, so we're just going to go ahead and say keep all your calculations in your calculator as a whole, and then the magic number of sig figs here is going to be 4. Okay, so make sure your final answer has 4 sig figs. So now that I have these two numbers right here, in order to get the average atomic mass, all I have to do is add them together. So I'm going to go 61.37 plus 24.186, and I end up with 85.556. And with 4 sig figs, I'm going to make that a 5.6 AMUs. Okay? This would be my average atomic mass. And if you recall, my original prediction was because the abundance of rubidium is for rubidium-85 is much higher than the abundance for rubidium-87, that the average atomic mass would be closer to 85. And yeah, it's much closer to 85. Okay? And there's another foolproof way of determining if you're doing something wrong, or a foolproof way to, is here's 85, here's 87. If my average is less than 85 or more than 87, something's wrong. Okay, you can't have an average, whether it be weighted or unweighted, that is less than the smallest value and greater than the largest value. So both of those cases are a good way to determine if you're making a mistake. Okay? So let's go and take a look at another problem. Okay, here we go. We have uranium has 3 common isotopes. If the abundance of uranium-234 is 0.01%, the abundance of uranium-235 is 0.71%, and the abundance of uranium-238 is 99.28%, what is the average atomic mass of uranium? So hopefully when you're looking at this and you look at those values, you know that your average atomic mass is going to be closest to 238. Why? Because of that overwhelmingly high abundance in comparison with the other two. Okay? And you also know that my average will not be higher than 238, but it will not be lower than 234, right? Because that's my highest and lowest value, and I can't have an average outside of that realm. Okay? Now, when you're doing these types of problems, like I said, it's always helpful to convert your percentages. So I'm going to do this right now. So be careful when you guys are moving your decimal places over. When I take this 0.01% and I divide it by 100, I'm going to get 0.0001, right? And then this 0.71% becomes 0.071, right? So 1, 2. Is that right? 1, 2. No, I get another 0 in there. Right. So 0.0071. Okay, and then this 99.28 would become 0.9928. So, do I have all the pieces of information do I have that I need to solve this? I do. I have the masses, and I have the abundances that are in frequencies. They're not in percentages. Now, here's another thing. Do I need to give you all of the abundance values? No, as long as I give you enough to get the third one. So for example, if I didn't tell you the abundance of uranium-234, you should still be able to determine this because you would have the abundance for 235 and you'd have the abundance of 298 or 238. Well, the difference from 100% would be your abundance of 234. Okay? So again, just to clarify, if I only gave you this guy and this guy, you'd still have enough information to solve this problem because you know that 100 minus 99.28 minus 0.71 is going to give you 0.01, right? So, enough of that. Let's go back to what we're doing. Okay, I'm going to go ahead and go my 234. That's my uranium-234, and I'm going to multiply that by 0.0001. Okay, my 235 equals 0.0071, or multiply time 0.0071, and my 238, which is the most abundant, is 0.9928. Okay, I'm going to multiply those products, or multiply those those numbers to get a product for all three. All right, so we got 0.0234, and then this is 1.6685, and lastly 236.2864. Okay, next step, add them all together. Okay, so I'm going to go 236.2864 plus 1.6685 plus 0.0234. My final answer ends up being 237.978 and like I said, we're going to 4 sig figs. So 1, 2, 3, 4. That 9 would of course be rounded up from that. That 7 would get rounded up that 9, which would make it be a 0. Changes that 7 to an 8. Okay. AMU. So my average here is 238.0. And that, of course, makes sense because 99.28%, that's a very high abundance. So your average would be very, very close. In this case, sig figs allowed them to be the exact same number. Okay. So what I'll go ahead and do is I'll put up one more problem. I want you guys to go ahead and try to attempt it at home. And then hopefully it'll help you with tomorrow, and you guys can use it on your in-class assignment. If you have any questions about it, then say something. So here we go. I'll go ahead and read it to you. Titanium has 5 common isotopes. Titanium-46, which is 8%. Titanium-47, which is 7.8% abundance. Titanium-48, which is 73.4% abundance. Titanium-49, which is 5.5% abundance. And Titanium-50, which is 5.3% abundance. What is the average atomic mass of titanium? So hopefully we should know that we're looking around here for our average because of this high abundance. Okay. And the other thing that I do want to kind of give you a little disclosure, sometimes I make these numbers up, which means don't look at the periodic table thinking, oh, that must be the average atomic mass because it's on the periodic table. Okay, that's not necessarily a very wise course of action because all you have to do is mess with these percentages, right, to change the answer. So I really want you to focus on knowing that knowing how to do this correctly, and not just keep referring to the periodic table to check your answer, because that doesn't necessarily mean that it's true. Okay, if you guys have any questions as to whether or not you are correct, talk to me and we'll get it figured out if you're not. All right.